This first video is on light waves of matter and should help you with sublevel 1 of the MOP connection, and it will help you fill in the answers for the classroom notes that you have. So let's go ahead and talk a little bit about the electromagnetic spectrum. Electromagnetic waves, if you remember, there were a couple of different types of waves. One of them were transverse and the other type of waves were longitudinal. And the only longitudinal waves that we know of are sound waves. So electromagnetic waves are transverse waves, and they're really capable of traveling through a vacuum, and they don't need any other material. So if you remember, sound waves need air. If you look in space, if you would travel to space and try to talk, nobody would hear you. But you could actually use a flashlight to communicate using Morse code. Unlike mechanical waves, though, that require a medium in order to transport their energy, we do know that these electromagnetic waves are able to just take their energy and transform it, or just transfer it through the vacuum of outer space. The electromagnetic spectrum, if you look at the diagram here, you'll see that there are some very long wavelength, very low frequency waves called radio waves. Just above that you have some microwaves, and just above that is infrared. The visible light we see is a very small portion of the EM, electromagnetic spectrum. Ultraviolet, X-rays, and gamma rays are on the other end, and if we had to determine which ones were really dangerous, we know that things that are dangerous tend to be on the right, and things that are not so dangerous by themselves are on the left. Lots of people get confused because microwave ovens cook our food, but that's because we concentrate a lot of waves all together. The common thing about all these waves is all of them have a speed of 3 times 10 to the 8th meters per second. So all the waves that you see here are traveling at the same speed, about 3 times 10 to the 8th meters per second. So another diagram down on the bottom that just shows you that radio waves have a very long wavelength, a very low frequency. Our frequency increases and our wavelength decreases as you move right, so that gamma rays have the shortest wavelength and the highest frequency. Diffraction involves the change in directions of waves, basically whenever they go through an opening or around a barrier. Water waves do this really well, so they can go around obstacles, and it's really obvious for water waves that are really long. So if you're out by a really big lake and a boat goes by, you can see the waves come in, and then if they crash up on the shore, you'll notice that they do it and they bend a little bit around piers or around anything that is down in the water. Electromagnetic waves work exactly the same way, and if you look at radio wave and microwaves, we know that those bend really well around different objects, and because they bend well around objects, we use those for communication. If we tried to use gamma rays, first of all, the gamma rays would travel right through everybody, and that would be bad. But the electromagnetic waves are really nice because they don't travel through you, they're not harmful, just in really small quantities, and they can travel anywhere about that they want to, so you can get your radio station whether you're inside or outside. The next slide here shows high frequency electromagnetic waves. So remember, the ones over here have a very high frequency. These are very dangerous. Ultraviolet causes sunburns. X-rays pass through you, and that's what we use to take pictures, but you really don't want to have too many X-rays in a year, or you can develop cancer symptoms and develop cancer. Gamma rays are very dangerous. Nuclear bombs, when they go off, produce a tremendous amount of gamma rays. Lots of gamma rays in space where we're not protected by the Earth's atmosphere and things from cosmic rays. The light that you see is also an electromagnetic wave. We start seeing light at about 620 nanometers, that would be red, and then it goes all the way down to about 390 nanometers, so very short wavelength. Anything that is on this side of red is what we call infrared, and anything that is on this side of violet is called ultraviolet. And they get their names from their frequencies. So infrared would have a very low frequency, very long wavelength. Ultraviolet would be a very high frequency, very short wavelength wave. Light and transparent materials. So if you remember when we played with the two tuning forks in the box, if I struck one tuning fork, the waves would travel from one box to the other and then make that other tuning fork vibrate. So light can do the same thing. Light can actually force different materials into vibration. If you've ever sat in a car when the sun is out, and you put your hand on the window feels very warm. It's because that light is absorbed by the window. Materials that transport or transmit light are called transparent. Glass and water are transparent. You can see right through them. These materials have kind of an elastic response to more vibrations at some frequencies than others. So those frequencies depend on the frequency of an electron depend on how strongly it is attached to a nearby nucleus. So this is kind of a molecule of glass, I could say, or an atom of glass, and you'll see that the electrons are really springy in that glass. That's important because when we have light, as it travels through glass, it actually travels from particle to particle. So here's 3 different atoms in glass. The light wave comes in, that energy is absorbed by the first one, and we say that it gulps up that energy. It gets full, and it can't take anymore, so it burps it back out. That goes to the second one. That second one gulps it, and then burps it to the third, and that gulps, and then it burps it. Because of this process, light actually travels less than c, and c is the abbreviation for the speed of light. So because of all these absorptions and re-emissions or gulps and burps, glass actually slows light down a little bit. And when it does that within the glass, it'll go slower than c, but then when it pops out the other side, it'll take back off again and travel at the speed of light again because it has all its energy back and the glass is not taking any more. We've talked a little bit about transmission. The other type of way we see light and see colors and things is through opaque materials. Materials that absorb light without any re-emission, so they don't allow that light to go through it and then kick it out the other side, are called opaque. So some examples would be wood, can't see through this, can't see through the stones, and then there's some people here, and you don't really see through the people either. Our atmosphere is very transparent to visible light and some infrared, but it's opaque to high frequency ultraviolet waves, where it's almost opaque. Most of the ultraviolet waves that get through the atmosphere are responsible for sunburn, so it's a good thing we have the atmosphere. Without the atmosphere, we would all be very, very crispy within a very, very short amount of time. Clouds are very semi-transparent to ultraviolet light, so you can go outside on a very sunny day or on a very cloudy day and still get a sunburn. So you see this gentleman down here has had that. If you sit close to the sand or water, ultraviolet light reflects from that, so you get kind of a double dose of sun. If you try to sit under a beach umbrella, a lot of people will get burned sitting under one. They've never been in the sun, direct sun all day, but between the water and the sand, they get a lot of that ultraviolet light coming back up and hitting them, and then that gives them that burn. And that is the end of light waves and matter.